So what we're doing right now is we're reducing down these fractions, right? We could divide this both by 100, so I would get 1/3 in question 1. Right? That's the reduced form. How about this one? Divide each of them by 25, and that's going to be 5. And what is this going to be? 18? Is that right? I believe. Yeah. Okay. And then 90 over 170. I think that would be 9 over 17. And then 18 over 24. Divide both by 6, so that would be 3/4. Cool. You've reduced your fractions, right? So that's kind of a topic that you would see in a math class. I know for sure. Well, it's kind of analogous to what we would talk about in chemistry. And an empirical formula is the most reduced form of that formula. So an empirical formula is basically a reduced form of a formula. Let me give you some examples of some empirical formulas. Let's take C2H4O2. What's the common factor between my numbers here? So if I divide each of them by 2, that would give me C1H2O1. And in chemistry, do I have to write the little ones afterwards? No, so realistically, the answer to this problem would be CH2O. That right there represents my empirical formula. Good. Or we could look at another example. N4O10. And I'll let you real quick come up with the empirical formula for that one. So find me the empirical formula of this compound. Okay, so on this problem, I think the way that we would have solved it is we would take N4O10, find that, what's our common factor here? 2. So this would become N2O5, and that of course would represent my empirical formula. What do we think? Good? Now what you're seeing over here to me is the easy way, or the easy questions with empirical formulas. Cool. Now I'm going to divide this up, and then I want to show you how the questions could become a little bit more complex. So now I want to spend some time talking about problems that involve some math, some serious math, in finding empirical formulas. So we can title this next little section, how to find empirical formulas from data. So using some data, how could we find empirical formulas? And let me show you how we do this, and I'll give you an example to show us. So here's going to be our problem. Let's say that I told you that we had a compound that was made of .0% potassium. The compound was also made of 14.5% carbon, and it was made of 38.5% oxygen. So let's say that that was the data that was given to you. So again, this right here represents the data given. And you were told to Find the empirical formula. Here's what we're going to do. The first thing I'm going to get you to do is divide up and create kind of like a table. So since potassium was the first element they mentioned, I'm going to put potassium right there, and then I'm going to put carbon, and I'm going to put oxygen. And then right below each of these guys, I'm going to put the percentages that they gave me. So what was the percentage of potassium? So I'm just going to write down that number, 47.0. I'm not going to write my percent sign. It doesn't matter if they give you grams or percents, on all honesty, so we'll see a problem in a little while that gives you grams and it won't change it. Let's see, carbon is 14.5 and the oxygen is 38.5. Perfect. So what have I done at this point? I've essentially just written down the numbers that they gave me, correct? Okay. Now here's your first step. Here's step one. So in step one, we're going to divide each by their individual masses. So divide each by their individual masses. So what is the mass of potassium from the periodic table? So 39.0, I believe 983, right? What's the mass of carbon? And how about the mass of oxygen? So I'm dividing each of them by their respective masses. Now if you don't have a calculator, you're of course always welcome to borrow one. But why don't you take a quick second and divide these out. Let's find that quotient for each of these respective elements. So again, now we're seeing that in step two, what we are doing is we are dividing each of these numbers that we had just received from the previous step by the absolute smallest of those numbers. So in this first case, what did we get? The number 1. And how about in the second case? At that rate, you're basically 1, right? Pretty as close to it as you're going to be, probably. So I say that's about a 1. How about in this case right over here? 2 point, what does it become? 1 point, or 2.001. Okay, that's essentially the number 2. Good? So here's our empirical formula. How many potassiums are we talking about here? Okay. How many carbons are we talking about here? And how many oxygens? 2? Right there. So KCO2, and that right there is our empirical formula. So we have found an empirical formula from data based on percentages of each element. How many steps were involved here? 2. In step 1, we divided by each molar mass, or mass of each element, and then in step 2, we divided by the smallest number we got before. Right? Let's look at another example real quick. I'll give us just a second to copy down some data. Rubbing alcohol is listed to contain 60% carbon, 13.4% hydrogen, and the rest is oxygen. Find the empirical formula. So kind of starting us off with some important data. They're saying, of course, find the empirical formula. First off, how many different atoms or elements are we talking about here?
3.
So the first one would be carbon, right? Then there's hydrogen. And what's the last one? Oxygen. You'll notice that they only gave us 2 percentages. They gave us a percentage for what? And they didn't tell you oxygens, but could you find oxygens? Yeah, because it's the difference from the 60 and the 13.4 plus 100, or from 100. So I got 26.6 for the oxygen, that's its percentage. The hydrogen, and I'm not going to use my percent sign here, is going to be what? Hydrogen is going to be 13.4. Carbon is 60. Cool. And now I'm ready to do step 1, correct? What do I do in my step 1? Okay, so why don't you find the mass of each one of these and divide it out, and let's see what we get after doing that. Let's check our work real quick. Is this what we had got? These numbers? Now, what is this? After we do step 1, of course, it's time for step 2. What do I do next? Absolute. And what is the smallest one? So 1.6626. It's got to be divided, or has to be dividing each of these. So 1.6626 at this spot, and 1.6626 at this spot. And then next, I'll let you do that, and then let's find those numbers real quick. So do those divisions, and then let's see what we get as far as that quotient goes. What are we thinking? Looks like this one might be C3H8O. So right there we might have our empirical formula. What are we thinking? Good stuff. So in question 2, they give you some percentages. They say it's 80% carbon and then it's 20% hydrogen. So how many different elements am I talking about in question 2? 2. So I've got to write out C, and then there's H over here. And write down their percentages. So that's going to be 80% for carbon and 20% for hydrogen. And what do I do in step 1? So divide by the mass of each of them. So that's 12.011 for carbon and 1.008 for hydrogen. So why don't you do that real quick? Let's do that. Okay, there's my quotients, if you will. That's what I divided. What do I do in this next step, which is step 2? Which would be which number, the left or the right one? So the 6.6606, 6.6606, and that's going to give me a 1 there. And right here, that gives me basically the number 3. So C H3. That's my empirical formula. Cool? Good? Good times? Okay. Let's turn over to the back. Let's look for a little bit more of a complex question. Okay, I want to do maybe number 5 real quick. No, I change my mind. Let's try number 4. Let's try 4 and 5. We got time for that. It says 30.5% nitrogen and 69.5% oxygen. So how many different elements are we talking about here? So let's write out an N area and an O area. And I'll let you fill it in with maybe these first two steps.
Whenever we're writing the vertical formula,
Mm-hmm.
we always put the number or the element that gave us first.
Mm-hmm. Typically the way that I do it. So I got my quotients after step 1 if you want to check and make sure that we're on the same page. And then I divide by my smallest one. Cool. NO2, is that what y'all got? Good stuff. Why don't you work independently real quick on number 5 and then for a special case of problem. So again, if you'll please just stop when you get to about this point on question 5. We about there? Good? No? Okay. Be identifying the smallest number out of this set, because you know we're going to divide by the smallest number in this next piece. A little hard to see sometimes. It's the last one, isn't it?
Yeah.
So 3.4064629, 3.4064 629, 3.40 64629. Let you divide those out real quick in your calculator. Remember, if it's very close to a full number, you just go ahead and write the full number. And like in this first case, that's pretty close to 1. The last case, of course, is going to be a 1 dividing by the same number. But how about that second number? What is it? Yeah. You can't have point or 1.333 in the formula. In other words, you can't do this. CH 1.3330. That's not going to be legal. What could we multiply, and this is the trick to that problem, what could we multiply each of these numbers by to get him back to a whole number? Like what if we take 1.333 and multiply it by 2? That's 2.666. That's not going to work. But what if we take 1.333 and multiply it by 3? What do we got there? Now that's pretty close to 4, right? So I could make him a 4, but since I'm multiplying everything by 3, because if you do it to 1, you got to do it to all, that would make the carbons 3, and the O's would be 3. So this would be C3H4O3. Y'all see how we got that? A little bit of a trick at the end, that if you don't get a whole number when you do that final division of the smallest one, multiply each of them by the same number to get whatever number is not close to whole. Yes, ma'am? It really is just a little bit of practice. Like I know that when you have a 0.3333, you're going to have to multiply it by 3 because 0.333 is basically like 1/3. I'll 1 up. What if it had said 1, 1, and 1.25? What would be multiplied by? 4, because 1.25 times 4 gives us 5. So we're always going for a whole number. Make sense? I think we could all agree that doing the problems kind of like this, where it doesn't have that little issue at the end, is certainly fair and simple. And then at the end, they might have just a little bit of an issue. Cool? The last remaining 3 problems are your homework. I suspect you could probably finish that now. And yeah, good luck.